Close your eyes. Picture this. You're standing at the edge of the universe. It's silent still. Then, boom, space itself trembles. A ripple. Not in water, but in space. Reality stretches, it squeezes. Waves spread out, huge, invisible. That's what gravitational waves are. Not just ripples, whispers. Echoes of cosmic collisions that took billions of years to reach us. And now, we can hear them. I still remember when I first heard about gravitational waves and the Nobel Prize for their discovery. It was huge. It felt like the universe itself had opened a door. Einstein saw this coming over 100 years ago. He said massive, violent events would shake space-time, like black holes crashing together, but for decades, it was just an idea, a ghost, until 2015.
Go back, a brief history of numerical simulations. This begins in the 1950s, motivated by Johnny Wheeler, my thesis advisor, who told us already in the 1950s that we should try to study the veritable storms in the fabric of space and time that occur when space and time, the geometry of space and time, are highly excited in a nonlinear fashion and rapidly changing. And we had, and he said, you go out and study this thing that I call geometrodynamics. We tried, we fell flat on our faces, we didn't have the tools to do it, but he recognized, and his students around him recognized, that in order to really do this, you had to do it numerically, so you had to begin to build the tools of solving Einstein's equations numerically on a computer or computer simulations. So the foundations were laid in the period from 58 to 64 by Charles Misner, Richard Lindquist, who are associated with Johnny Wheeler, Susan Hahn, who was a computer scientist at IBM, who teamed up with Richard Lindquist to start this out. This is the best photograph I can find of Lindquist in that era. It was not, however, until 1978, the first successful collision simulation was done of head-on collisions of two black holes by Larry Smarr and Kenneth Epley, building on foundations laid by Bryce DeWitt and earlier foundations of Misner, Hahn, and Lindquist. And there are a number of other contributors in this period. I'm highlighting the people who were really the giants in this early era. So here, 58 to 78, this is 20 years already, the struggling to get this started. Next was the problem of doing two black holes that circle around each other and spiral together, collide and merge. And the community began to work on that, and it became a very concerted effort by 1983 when we were co-founding LIGO, and we were telling our colleagues doing these simulations, we really need these simulations in order to extract information from the waves that we will see. By the 1990s, there was something called the Binary Black Hole Grand Challenge Alliance, led by Richard Matzner at the University of Texas. All of the world's experts in this getting together and working in a concerted sort of a way. And I became a little concerned that it was going more slowly than it should be, so I made a bet. I like to make bets. I made a bet that I hereby wager that LIGO will discover convincing gravitational waves from black hole coalescence or merger before the numerical relativity community has a code capable of computing waveforms. I wanted to lose this bet in the worst possible way. I wanted to lose this bet. By the early 2000s, I became alarmed. The progress really was slower than the experimental progress. Why was it slow? It's been really hard. You're trying to simulate not two things that collide in space and time. You're simulating things that are made out of warped space and time that are colliding. So you don't have an arena in which this is going on. You're simulating the arena itself, a warped arena in which this is going on. And so by the early 2000s, I became alarmed. And so I started, in collaboration with Saul Tukulski at Cornell, what we call the SXS collaboration to work in this field. Saul had been working on this already for a few years. In 2004, the first successful simulations were done by Franz Pretorius, a postdoc in our group, Joan Centrella, Manuela Campanelli, and their research groups. By 2014, the simulations were mature enough for the first LIGO observations. And I conceded the bet with great happiness. And when this first signal came in September 14, 2015, the numerical relativity gravitational waveform is the red here. The observed waveform is the gray, and that matched beautifully. And by comparing those waves, the theoretical and the observational with each other, we inferred the properties of the black holes and the distance to the sources. You can then go back, knowing from the observations and the comparison of the theoretical waveforms with the observational waveforms, you can go back and look at the simulations and see what was happening during those simulations. And this is a simulation of the colliding black holes as seen from outside our universe, looking in on the warped shape of space and time around the black hole. The red is the slowing of time. The arrows are the dragging of space into motion. It's a gigantic splash in the shape of space and the slowing of time. And then an oscillation, the gravitational waves go propagating out. You can also compute what it would have looked like to your eyes if you had seen the two black holes go around each other, collide and merge, creating what's called gravitational lensing, distorting the star field that's behind the two black holes.
That's when the universe whispered, and we finally had the tools to listen. LIGO, the Laser Interferometer Gravitational Wave Observatory, heard the first wave. And just like that, the universe spoke, and we listened. Everything changed. Let's talk about that first signal. It came from two black holes, monsters, one 29 times the mass of the sun, the other 36 times. They danced closer and closer. Then, boom, they collided. 1 billion years ago, 1.3 billion light years away. In a fraction of a second, they merged. 3 suns worth of mass turned into pure energy. It rippled outward, gravitational waves spreading through space and time. And those waves? They stretched space by less than the width of a proton. But we caught them. We heard the scream of the universe, its raw, violent cry echoing across time. And it gets crazier. Gravitational waves don't just tell us about collisions. They're a new sense, a way to listen to the universe. Before this, we could only see light. Telescopes showed us stars, galaxies, and black holes. But now, we can hear them. It's like staring at an orchestra, and suddenly, you can hear the music. And the sounds, they're wild. Black holes colliding, neutron stars smashing into each other, and maybe, just maybe, signals from things we can't even name yet. Gravitational waves aren't just proof that Einstein was right. They're a new way to explore the universe, a new branch of astronomy, and we're just getting started. But what do they really tell us? Space-time isn't fixed. It bends, it ripples, it moves. Reality itself shifts and flows. Think about that. Reality isn't solid. It's alive. And that raises big questions. What if these waves are more than ripples? What if they're fingerprints, traces of destruction and rebirth? Could they hold clues about the first moments of the universe, or cycles of creation we can't even imagine? And here's the big one. Could gravitational waves help us link gravity and quantum mechanics? Are they the threads stitching reality together? If space-time ripples, could it shatter? Are these waves signs of cracks in the universe? And if those cracks exist, what's on the other side? What if these waves aren't echoes from the past, but warnings from the future? What if they're messages, codes written into space-time itself? Could they be signals left by other universes, brushing against ours, colliding, or even merging in ways we can barely imagine? Or whispers of civilizations long gone, or yet to come? And no, this isn't science fiction. Look, even as a physicist, I believe in God, but not as some guy sitting on a cloud. To me, discoveries like this don't threaten my faith. They deepen it. They make me wonder if science is just another way of listening to something bigger. But hey, that's a conversation for another time. These questions aren't random. They're grounded in cutting-edge physics. Einstein's theory of relativity laid the foundation, but modern physics pushes it even further. Quantum gravity suggests space-time might not be smooth but grainy, like foam at the smallest scales. String theory proposes extra dimensions curled up beyond our perception. Cosmology explores the possibility of a multiverse, an infinite collection of universes, each with its own rules. Wormholes? They're serious candidates for shortcuts through space-time. Scientists are searching for clues, not in science fiction, but in equations, experiments, and data. These ideas live on the boundary between what we know and what we don't. Could these waves unlock dark matter? Maybe they carry echoes from the dawn of time, traces of inflation when the universe expanded faster than light. Could they reveal cracks in reality, gaps where quantum and classical physics collide? Or point to hidden dimensions, paths to places we've never dreamed of? Wormholes, alternate realities, or signals from civilizations so advanced they've learned to weave ripples into messages across time and space. Think about it. Imagine ripples so small they slip between atoms, bending time as easily as light bends through glass. Imagine waves echoing from the first moments of the universe, or the last. What if they're signals not just from the past, but from something waiting in the future? What if we're not just listening to the universe? We're hearing its heartbeat, its warnings, its secrets. And if this hit you, like the ground shifting beneath your feet, then hit subscribe. Let's dive deeper. Let's chase these ripples to their source. What if the next wave we hear isn't just an echo, but an answer or a question left for us by something we can't yet name? What if the universe isn't just speaking? It's waiting for us to respond. All right, that's going to do it for Gravitational Waves. Thank you. Stay curious, stay hyper-focused, and let's keep exploring the unknown. Bye.